Okay, so yesterday, kind of what we were talking about is how to approach proofs on alternating series. And so we said that in general, when you have an alternating series, the normal problems are ones where you have -1 to the k times all power functions over power functions, or -1 to the k, or like -1 to the k plus 1 times exponential over exponential. So when it's -1 to the k and then everything else is all the same type of function, that's the type of series we've been dealing with, or that's what we were dealing with yesterday. And they follow three basic formats. You have the series at the beginning, and so if you have the sum ak, um, you split it into kind of three parts. So you say, okay, we're going to consider the absolute value of AK, and then you compare that to something else that's easier. And so if you have a power function over a power function, then the one on the right is going to be a P series. Or if it's exponential over exponential, it's going to be geometric. Does that make sense to everybody? Okay, that you're going to conclude whether then that diverges or converges. If this converges, then the one in the middle automatically converges. And the proof is going to be either the direct or limit comparison test. Okay. And it's not, a lot of times you can just use the limit comparison test if you want. There are some cases where you can use the direct comparison, but in these problems where it's power function over power function or exponential function over exponential function, then you can always use the limit comparison if you want to. It's sometimes quicker to use the direct comparison if it's easy for you to tell. But regardless of which test you use, if the one on the right converges, the one on the left converges. If the one on the right diverges, then the one on the left, or the middle one, my bad, not the far left, but the one in the middle diverges. And it doesn't matter which test you use, that does not change that conclusion. Does that make sense? Any questions so far? Okay, if the one in the middle converges, so if both of the ones on the right converge, then what does the original series do?
Converge.
Converges. And so it converges absolutely. And then the thing that we would use is by the absolute convergence theorem. Which is a little weird because it sounds like the answer, but the name of the theorem is almost the same as the name of the answer. So it converges absolutely by the absolute convergence theorem. If the middle one diverges, then the one on the left is going to converge unless the limit of the sequence is not zero. So as long as the limit of the sequence is not zero, or is zero, this will converge conditionally by the alternating series test. Does that make sense to everybody? What if AK does not go to 0? Then what happens? If AK does not go to 0,
Diverges.
then the whole thing diverges. By what test?
K-term.
By the K-term test, or the test for divergence. Good. Okay. Does that make sense to everybody? Everybody clear? Now, the alternating series test actually has 3 conditions. So when we say if AK goes to 0, that's one of the 3 conditions. The 3 conditions on the alternating series test are, first, that the BK part. So if you get rid of, like, AK is the same thing as -1 to the K or some alternating term times BK. So the alternating series test says that BK needs to be positive. That's going to be the case if it's actually an alternating series. Maybe on some weird problems, BK would be like all negative, but you could factor a -1 out and make it so that it's all positive. And then, so BK is going to be all positive. The second condition is that BK goes to 0, which would then in turn means AK goes to 0. That's what we're saying has to be true. The third condition is that AK is decreasing, or BK is decreasing, not AK, but BK is decreasing. And just real quick, we kind of explained that yesterday by saying, if you have a positive sequence that goes to 0, chances are it looks like that, which means if it's positive and going to 0, chances are it's decreasing. The only way that doesn't happen if it's positive and goes to 0 is if it's like bouncing and still like closing in on 0 like that. But if you have functions like this, where it's all power functions over all power functions, or all exponential functions over all exponential functions, that's not possible. You're not going to get a graph like the one on the right. So if it goes to 0, then it's going to be decreasing if everything's positive. And so that's why it's enough when we're thinking about it to see that it goes to 0. That means it's going to converge. If it was real weird, that's not the case. But if it's real weird, we're probably not going to approach it this way. We're probably going to use what's called the ratio and the root test, which we'll get to later today or probably Monday. Does that make sense to everybody? Any questions? This is like a big part of what we've been doing. The stuff that we did before yesterday is just the right-hand 2 columns. So like on series 3, we're talking about series that look like this. So on the series 3 handout, we're already at the absolute value. So we don't like have to take the absolute value because it's already all positive, but you're doing these right-hand 2 columns. We're dealing with this and this, and you don't say consider absolute value. It's just that's the original problem. Series 4, the first 10 problems, you're dealing with all 3 of them. And if you go back and look at those 10 problems, all 10 of those fit into one of these 3 categories, either this blue one where they converge absolutely, the green one where it converges conditionally, or the purple one at the bottom where it diverges by the K-term test. Does that make sense to everybody? Any questions so far? You guys good?
For the statement in green, do we also need to do like, do we need to show that A of K goes to 0?
You
or
do,
can it just
or
be
at least
assumed?
you need to say that. You need to say it. You may not have to do a huge proof. The proof that actually requires some work is a lot of times the decreasing part.
Okay.
All right. Other questions? Okay. And so what I want to do is I want us to figure out, without writing the steps of the proofs, I want to do one with the alternating series test here in a little bit, where you have to actually do a little bit more to prove the decreasing part of the problem. But what I want to do is kind of what we were doing a couple days ago, where we just put up a series and we said, okay, what is the answer? Does it converge conditionally, converge absolutely, or does it diverge? And then what tests would we use? So we might say, okay, we're going to use the P-series test, or we're not really P-series test, but we're going to say, okay, P-series. We're going to use a comparison test, and then we're going to use absolute convergence theorem. And then it converges absolutely, or P-series comparison test and alternating series test, or just K-term test. So just list the tests we would use. We don't need to distinguish which comparison test, because that you can figure out if you're doing the entire proof. So we don't need to distinguish which comparison test, but that it is a comparison test. And then do distinguish whether it's p-series or geometric, whether it's absolute convergence theorem, alternating series test, or k-term test. So on these, just what is the answer? Meaning converge absolutely, converge conditionally, or diverge. List the tests used without showing the details of the tests. Okay, and so number one is the sum k equals 0 to infinity, -1 to the k squared over 8k to the third plus 27. Man, struggling. All right, so let's try those. So just an answer, list the test. I'll give you a couple minutes and then we'll talk about them. Okay, let's look at a few of these. So, or let's look at them. So on number one, you would take the absolute value. You would then compare to a p series or the harmonic series because you get k squared over 8k to the third. So on these, it's not like you can't write anything, but the only relevant thing is really, as far as determining the answer, is what happens over here. And so the fact that it's 1/8 times the sum 1 over k means that this is going to, on the right, it's going to diverge. And so you can either say the harmonic series or a p series. and the conclusion would be diverge. That's on the far right. On the middle, you use one of the comparison tests, and we could figure out which, but that's going to diverge as well. And then on the far left, it's going to converge conditionally, which will be the answer, but we'll use the alternating series test. But the actual conclusion will be that the series converges conditionally. Does that make sense to everybody? Any questions on that? Okay, and like so what we're listing over here is like on the far left, we've got that. We're going to list, okay, harmonic is the first thing we'd use, and we'll say, okay, that means that part diverges. The comparison test is going to conclude that the absolute value diverges, and then the alternating series test is going to conclude that the original converges, which means the original series converges conditionally. Okay, so do a different color, just separate it. But on the second one, actually the same thing's going to happen. So on the far right, we're going to get k over k squared, which is 1 over k. And so we're going to have the harmonic series or P series. It's going to diverge. We're going to do a comparison test. It's going to diverge. And then we're going to do the alternating series test, and it's going to converge, which means this is going to converge conditionally. Any questions on why, or any questions on how to figure that out? All right. On number 3, if you get over to this point, we're going to get the square root of k squared over k, which is actually the sum of just 1 because it cancels completely. So what happens when when we get that?
The k-term test applies.
Yeah. So this is the k-term test, or the test for divergence, and the answer is diverges. Does that make sense to everybody? That's good. All right. And then on the next one, by the time you get over to the far right, you're going to get the square root of k over k squared, which is 1 over k to the 3 halves. So that's going to be a P series that converges. Then the comparison test in the middle, it's going to converge. And then the one on the left is going to converge absolutely by the absolute convergence theorem. And so that converges as well. And so the conclusion, or the answer, is going to be converges absolutely. Does everybody follow that? Any questions on that? Okay, on number 5, when we get over here, we're going to get k over k to the 3 halves. That's 1 over k to the 1 half, which means we're going to get a P series that diverges. We're going to do a comparison test that diverges. And then the alternating series test is going to conclude that the original series converges, which means this converges conditionally. I want to put a few more of these up, but any questions on the first 5? Well, I changed to blue and switch back. Everybody good? Okay. So if I go and do a few more, so same directions, just what is the answer, and then does it converge or diverge? So converge conditionally, converge absolutely or not at all. So let's say I have -1 to the k times 3 to the k plus 7 over 4 to the k minus 2 to the k minus 8. I'll make that 3 to the 4k. And let's do Okay, so let's do those 4, and then we'll talk about them again in just a minute. Okay, so when we're doing these, on the first one, when you get over to the right, you're going to end up with 3 to the k over 4 to the k, which means the 3 to the k plus 7 over 4 to the k, which means you're going to get 3 to the 7th times 3/4 to the k. And so that's going to be a geometric series that converges. You're going to do a comparison test in the middle. And the comparison test is going to show that the absolute value converges. And then the absolute convergence theorem proves that the original series converges absolutely. Everybody clear on that problem? That's good. Okay, on the next one, on the far right, you're going to get 3 to the k plus 17. I'm sorry, 3 to the 4k plus 17 over 10 to the 2k minus 1. That's 3 to the 17th over 10 to the negative 1 times 81 over 100 to the k. And so that's going to be a convergent geometric series. You're going to do a comparison test, and so it's exactly the same as number 6. Comparison test, and it's going to converge, and then the absolute convergence theorem is going to prove that it's going to converge absolutely. Everybody clear so far? That's good. On number 8, when you get over to the right, you're going to end up with 3 to the 17 over 9 to the 1st times 81 over 81 to the k. And so what's weird about that? Or what does that tell us? So that's going to diverge because of the k-term test. So the limit of the sequence there is not 0. So then the whole thing diverges. Is everybody clear why? Any questions? Okay, and then, so the idea is like when you're doing these 8 problems, like all the stuff we're doing within the proof is, and we've kind of said this a little bit before, but all the stuff you're doing in the proof is not really for you to determine what the answer is. It's more, you know, the answer already. And then when you're showing the stuff within the proof, you're proving that you're correct. And so what we're listing here is the structure of the way you would want to set up your proof. So like when you have these 3 parts on most of them, you're going to divide it up into 3 parts like what we're doing here. And I do want to go through one again, but like what we're doing yesterday and like you're doing on the first 10 problems on that worksheet that you were working on last night, or you need to work on between now and next week. On number 9, What's different about number 9? So it's not exponentials, but what's different about number 9 versus these first 4 even? Somebody.
Not going to alternate.
Yeah, it doesn't alternate. So on
Okay.
this one, you just start with comparing it, and you compare it to 3k over 5k squared, which is 3/5 times 1 over k. And so you're going to do the harmonic series, which diverges. You're going to do a comparison test and prove that it diverges. But then there's no alternating series test part of this because it's not an alternating series. So you only have the 2 parts, and that series diverges. So this problem 9 is like the stuff you're doing on the series 3 packet. And all of you, or most of you who were doing that, I think were probably getting a problem like problem 9, no problem. The issue sometimes that happens is you get so used to doing these that are alternating, and people will do like number 9 on the test and then jump back and say, okay, it converges conditionally by the alternating series test. And so like on number 5 or like on number 4, where you would do that. And you just have to be careful because it's not actually an alternating series. So you don't have that part on the far left. You only have the series itself and the comparison series. Does that make sense? If I threw a -1 to the k in front of this, if it was -1 to the k times this, then that series would converge conditionally. But this series that's not alternating diverges. Everybody clear? Any questions so far? Okay. All right, so I want to do the entire proof for one that's a little bit harder than the ones we were doing yesterday. So entire proof for this one. So let's do number 1 is going to be the sum k equals 2 to infinity of -1 to the k times 6k over, let's do 3k squared minus 1. Okay. So when we do this problem, what's the answer? So before we do anything, does this series diverge? Does it converge conditionally, or does it converge absolutely?
Converge conditionally.
This converges conditionally, and we should know that by looking, because the series you're going to end up with on the far right is going to be 1 over k. Is everybody able to see that by looking at that problem? So you're going to get, on the far right, we're going to get 1 over k. That means that's going to diverge because it's the harmonic series. Then we're going to do a comparison test, and it's going to diverge because of the comparison test. And then this is alternating, and it does go to 0. The sequence goes to 0. So this is going to converge conditionally by the alternating series test. So we should know the answer and the basic structure of the proof. We should know all of this stuff that we're writing up here. We should know that before we write anything, really. Or at least once we're writing the P series, the harmonic series on the far right. We should know the structure of the proof. The only thing we might not know ahead of time is which comparison test to use, because that doesn't affect the structure of the proof. It just affects like the details of that middle part, but we can figure that out as we go. So then we're going to do this kind of, we're going to determine the series in reverse order, and then we're going to go back and prove them from right to left. So we're going to say first, okay, consider the absolute value. So the sum of the absolute value of AK, that is the sum 6k over 3k squared minus 1. Okay, so we're going to consider that. We're going to then compare to the sum 6k over 3k squared, which simplifies to 2 times the sum 1 over k. That diverges, and our rationale is that it's a constant multiple of the harmonic series. Everybody clear to there? Any questions to there? Okay, now on the one in the middle, we're going to use a comparison test. So if you don't want to determine whether you can use the direct comparison test or not, you can just use the limit comparison test. Here, the one on the right diverges. So what we think in our head is that the series increases to infinity. Everything's positive, so it goes up forever. So the one in the middle, we would like it to be larger than the one on the right. Is the one in the middle larger than the one on the right?
Yes.
Yeah. Yes, because the bottom is smaller. So we can use direct comparison, which is quicker than limit comparison, but not that much easier. So I would say, okay, 6k over 3k squared minus 1 is bigger than 6k over 3k squared. And in turn, that's bigger than 0. So the sum of the absolute value of AK diverges by direct comparison. Does that make sense? Okay, now the one on the left, because it's not a k-term test problem, it's going to converge conditionally by the alternating series test. So we go through the alternating series test. So when you're doing the alternating series test, you say, okay, BK is the non-alternating part of that series. Most of the time, that's the same thing as the absolute value. And pretty much always. So you prove 3 conditions on the alternating series test, and those are listed on that sheet for you. The first one is that BK has to be positive, or at least it needs to be positive for large K. Check to make sure that's true. So from 2 to infinity, 6K is for sure positive. 3 times K squared is positive, and it's actually bigger than 1. So when you subtract 1, it's still positive. So the whole thing's positive. The second thing is the limit of that needs to be 0. So we're going to write 6k over 3k squared minus 1 approaches 6k over 3k squared, which approaches 2 over k, which as a sequence approaches 0. Okay, if that weren't true, then it would have been a k-term test problem. The third thing is that BK is decreasing. And there are several ways to show this. On the examples we did in yesterday's class, the formulas were a little bit simpler because the numerator was a constant. And so you could just compare the formulas and clearly see which one's smaller. Here, because the numerator and the denominator both have k's in them, it's hard to compare them directly. So there are a couple ways to do this. If you go back and watch the video on the monotonic and bounded sequences, I go through on that how to show that a sequence is increasing or decreasing a few different ways. One way to do it is to convert it to like f of x. So we would say like let f of x equal 6x over 3x squared minus 1. And then how can I use that to prove that the sequence is decreasing? What should I do with that? Prove that.
Take the derivative and see if it's negative.
Yeah, so take the derivative and prove that it's negative. So we do f prime. So that's the quotient rule. So you do the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And so that's 18x squared minus 6 minus 36x squared over 3x squared minus 1 squared. That's negative 18x squared minus 6 over 3x squared minus 1 squared. That's less than 0 because the bottom is squared, so it's positive. Negative 18x squared is for sure negative because x squared is positive when you're going from 2 to infinity. And then you're subtracting 6, that's negative. So you have a negative divided by a positive, which is negative. That's a proof that BK is decreasing. So the original series, negative 1 to the k times 6k, over 3k squared minus 1 converges because of that. It converges conditionally because the absolute value diverged. And we would say that's because of the alternating series test. Any questions to there? You guys good? Okay.